Okay, let's start turning your homework. And if you would put Wednesday's date on it, please. That was the 20th. So we'll keep it as Wednesday's date. Okay, I turned the exams in to scanning this morning, and they should have the results back to me this afternoon, and I'll crunch the numbers and put an announcement up on Blackboard sometime the next day or two. And then you'll be able to see your score, and then we'll go over some of the exam on Monday. Okay, so we're going to move on to Module 6. So Module 6 is about what's called rational functions. Okay, so rational functions, we're going to take a lot of what we did from polynomial functions to talk about rational functions. So remember that a polynomial function was something like this, you know. I'll just write it out. Three x to the 8th minus 4x to the 5th plus 20x squared plus x minus 2. Okay, so there's an example of a polynomial function. So a rational function, it's used this word ratio. So basically a rational function is just the ratio of polynomials. So basically we just take one polynomial and we take another polynomial and we make a big fraction out of it, and that creates a new function, and that's what we call a rational function, and it's named by this root ratio. Okay, so for example, Okay, so it's the ratio of P over Q, where P and Q are both polynomials. In analyzing these then, it's much of what we did with polynomials is going to be the same, especially all the features of this polynomial in the numerator, all that we learned about how to understand polynomials, all this, what we learned about the features of this polynomial in the numerator will be reflected in the rational function. So what's new is this polynomial that's in the denominator. That's really what brings a new element to these rational functions from polynomials. Okay, and so that's what we're going to be focusing on at first, and then on Monday we'll talk about just in general graphing rational functions all together. So we'll use what we learned about polynomials to look at the polynomial in the numerator, and then what we talk about today, which is this polynomial in the denominator, because that's kind of the new feature to these functions. Okay, so in order to do that, you're going to work on Module 6, Worksheet 1. Numbers 1 and 2. Let's just do number 1, and then we'll talk, and let's go through number 1. So number 1, which is page 229. Okay, when you get to part C, is that the table, part C? Start in the row where x equals 1. That's in the middle of the table. And then work your way up the rows. So start at the middle and work your way up the rows. And you don't have to do the rows below 1. So start at 1 and work up. And then once you get to the top row, just go on to part D. Okay? You can ignore the rows below 1. Okay, so it's crucial that you get everything right before you go on, or else you'll just do a bunch of work digging a hole for yourself because something before was wrong. So I definitely encourage you to work with each other, check what you're doing, check your work, and then also I can come around, and if you want me to check something, I can check something for you also. So read carefully. You're just doing this page, basically, number 1 on this page. Work together. Okay, this is last chance to get the homework in. Everyone's doing your homework. Can you turn that off for me?
Oh, I'm sorry.
Last chance for homework. Let's think about it. So if you spent $20 on gas, you want to know how much you paid per gallon. You divide by how much you paid each month, or do you divide by how many gallons you bought? So they're saying it's not arbitrary change. It's just average cost per gallon. So it's not the average rate of change. So does the cost, every time you buy a gallon, you're going to multiply 3 million by
Plus, right?
plus what?
Plus the 390 to the X cost. That'll give me the cost of the fuel.
So if you buy 4 gallons, to get the cost of 4 gallons, you're going to take 390 multiplied together 4 times. Cost of 4 gallons.
I would be multiplying 2 times the pound.
That's good. That's good. What else have you done this? We want the cost per gallon. The parade will start now. Here starts the parade. Are you going to be part of the parade today? Or not? Total cost of fuel. So it's the yes, so you want the total cost per gallon.
This would be gallons.
Yeah. So how would you write that function? How would you write that function? Okay, so most of you got this for the total cost for part A. Make sure you got that right. So then part B is that's kind of the center, the main function for this problem. So how do we find the average cost? We're going to call that G. Average cost per gallon. So if this is what you're paying for X gallons, total for X gallons, how would you get the average you're going to pay for each gallon? Divide by 3.9. That gives us how much we pay for each gallon. Okay, divide by X has been offered up. So are we going to divide that by 390 or by X? What would make sense? What's that? Yeah, so if the total cost, we want to divide it by how many gallons you bought, and that will give you what you paid on the average for each gallon. Make sense? So you're going to take that function f of x. Many of you did this already. And you're going to do what to it? Divide it by x. Then it asks, so then what is a domain of this function? Meaning, what are valid values of x? He said all positive. What about negative values? What is x? X is number of gallons of gas. So can we have a negative? No. So then, can we have a positive number of gallons? Of course, okay. So then the last thing is 0. Can we have 0 gallons in this formula?
No.
So we can have 0 gallons. We can absolutely have 0 gallons. But in this function, 0 would not be permitted, you see? Because it would be trying to divide by 0. Okay? So in the total cost, 0 is fine. So we can have 0 gallons, and then we're gonna, if we pay our startup, we pay 3.2 million. But for the average, for the G function, we have to be strictly greater than 0. Although 0 gallons makes sense, it's not permitted in our average cost function. Okay, so now you're going to build that table. Start with row 1 in the middle and work your way up the table. And you can disregard those bottom 3 rows. Is it $4.90 a gallon? $3.90? Thanks. Okay, check your numbers with someone next to you. Check your numbers. And the important questions are below the table. That's really the point. Those questions below the table. See if you agree with what I got. Agree with what I got?
You have an extra 0 in your formula. Would that make it come out wrong?
Well, my table is not based on my formula. Do I have an extra?
Okay.
Yeah, no. I just did these by myself, so. You're right. Thanks.
No problem.
There we go. Okay. Okay, let's talk about this. So we agree with the numbers I got in my table? Agree with yours? So if we buy 1 gallon, does it make sense that the average price is about $3.2 million for that gallon, or per gallon? Yeah, because we bought 1 gallon and we spent $3.2 million for it. So if we buy a half a gallon, about how much did we spend for that half a gallon? About how much did we pay for that half a gallon of gas over total? Yeah, about 3.2 million. So, but that was for half a gallon. So what are you paying on average for a whole gallon? So you paid 3.2 million for a half a gallon, right? So what on the average then, what would you pay for a whole gallon? Twice as much as that, right? Because at that price, to get a gallon at that price, you'd have to buy 2 halves, and it would be twice as much. You see, per gallon. So no matter how small an amount of gas that we purchase, we basically pay 3.2 million for it. So here I'm paying 3.2 million for 1/100th of a gallon. So what am I paying per gallon? A 100 times that. You see, I'm paying 100 times as much per gallon because I paid 3.2 million for a 1/10 of a gallon, or a 100th of a gallon. So to get a whole gallon, on the average, I'm spending 320 million per gallon. And so what happens, this right here, a sequence of values like that is represented by this notation here that you saw. X is getting closer to 0, and then what does the plus mean? Yeah, from the right, or from values greater than 0. So if you, on the number line, if you look at 0, we're approaching 0 from the right side with positive values getting smaller to 0. That's what this means. So approaching 0 from the right. And as we approach 0 from the right, or as the amount of gas that we buy gets really, really small, what happens to how much we're paying per gallon? What is that? Yeah. So is there a limit to how big that average cost could be? No, what's happening to the average cost? It's increasing. What if I did 1/1000th of a gallon? 1/1000th of a gallon. What would my average cost now be?
0.03.
No, 3.2 billion, right? Is there any limit to how great this average cost can get? No. As long as we take a smaller and smaller portion of gas, this average cost per gallon is just skyrocketing, okay? So how do we represent that? So as x approaches 0 from the right, what does g of x do?
Get closer to infinity.
Yeah, it's going to just whirl off to infinity. Okay, so let's see this graphically. So right now, I'm graphing this first point, 3.2 million. I'm graphing it as a red point. Why can't I see it? So what am I going to change? How am I going to change the y-axis? I got to zoom way out, right? Right now I'm in the tens. Now I'm in the hundreds, thousands, 100,000s. There it is. So now 3.2 million, average cost for 1 gallon. Okay, average cost for 1 gallon. All right, so now I'm going to plot the next point. If I buy 1/10 of a gallon, or sorry, half of a gallon, okay, why can't I see? So I just changed my x scale. So I can't see this point. I've just graphed the point for half a gallon with an average cost of 6.4 million. Yeah, I got it right. I got to zoom out on the y even more. So there it is. So this is what we said. What we said was as x approaches 0 from the right, the value of the function is increasing. So what's the next point? 1/10 of a gallon, average cost, 32 million. There it is. Again, as x approaches 0 from the right, this average cost is going up and up and up. One more. I got to zoom out again. Oops. There it is. So we're getting a feel for what the average cost does as you buy less and less gasoline. This average cost is, what are you saying? It's increasing without bound. It's just, there's no limit to how great it could be. And that is like approaching infinity, approaching infinity. Okay, so can you imagine what that graph's going to look like? Let's graph it. I'm going to graph. And what was our, for this average cost, what was the domain that makes sense for the average cost function? Yeah, so everything greater than, include 0 or not? We don't want to include 0 because you can't divide by 0. Unless you're Chuck Norris. Chuck Norris can divide by 0, but we can't. Okay? So this is what this graph is doing. As we get closer and closer to 0, that average cost is skyrocketing to infinity, and that's then what our graph looks like. So how does this relate to rational functions? Look at the function g. What's the function g like? Yeah, it's a ratio, and so this is linear. They're both linear functions, but linear functions are polynomials. They have degree 1. They have just the highest power of x is 1, but they're still polynomials. So this is a rational function. And remember, we talked about roots. Roots are points of interest, and roots are values of x that do what? Remember what roots are? Values of x that make a 0. So those are points of interest. So what's our point of interest for this but just looking at this as a polynomial, just this value x, what is our root? 0, right? So our root is x equals 0. So that's our point of interest. And so what's happening is since x can't be 0, as we get closer and closer to 0, it's like it's like the function saying, you can't do that. And so it goes haywire, right? So it goes haywire. It's like, you can't plug 0 into this. So if you start getting close to it, it's saying, what are you trying to do here? You're trying to put 0, and I won't accept 0. So things just go haywire. And that's the idea of what we call, so we've got this vertical line that the graph is what can get closer and closer to, but it can never cross, right? It can never cross that because x can't be 0. But as we know that it'll get, as x gets less and less, the value of g will just get greater and greater. So this is the idea of a vertical asymptote.
So then, if you had, say, a function with a different root, like say the root was 1.
Yeah, we're going to do that down here. Yeah, we're going to do that next. Yeah, we're going to do that next. Okay, so this vertical asymptote, it occurs where you have a root in the denominator. Because it's like, as you get closer and closer to that, it's like you're trying to plug 0 in, and we see from this gas example, we see the behavior that as our number of gallons got smaller and smaller, trying to look like it's trying to get to 0, that average price per gallon just heads to infinity. It just cruises up, and so that's the idea of a vertical asymptote. Okay, so now I want you to work number 2. And so next to part D, word part, just write a little note to yourself and write build a table. So on part D, you're going to build a table. So it's up to you now to figure out what table applies to that question. Okay? So work together on these questions. Talk amongst yourselves. Okay, find someone to compare with. Whatever work you're doing, compare your answers to A and B. The function in part C is the important thing, and A and B is helping you to build that function in part C. So check your work with somebody. So what the ratio of flavoring to water. Flavoring in the numerator, and water's in the denominator. So make your ratios fractions. Lots of you using the colon. Make a fraction because our function is going to be a ratio fraction. So you want flavoring to water. What is 7? 7, how much water do you have? So you have 1 fraction. So make those ratios a fraction form. Flavoring in the numerator, amount of water in the denominator. Yep. Okay, so flavoring to water. Look at these right first. How much in the first example, how much water is there?
7
No. Just carefully. Not 7 gallons of water. See? Yep. Yep. That's what you're getting at. You didn't do here. What did you here? Look at it again. What does X mean? X is what? Right. What's the denominator? Total volume of the mixture? Right. So you did it right here, but then you did something different there. Yeah, those are right. Okay. These are just examples. Now you have X as any total amount of mixture. So your ratio is going to be based on X. Yeah, got these right. Just apply the same thing here. Now if X is any amount, what would the formula be? That looks good. That looks good. So just do whatever you did here. Do the same thing here. So X is your total amount. What's this your total? What's the 2 and the 13? How'd you get the 2 and the 13? We did something to get those numbers. Right. Exactly. Exactly. The rule will look like that. It's going to be the ratio of flavoring to water. Oh, that's right. How do you get how much water? It's this. So the output of our F function is going to be the ratio of flavoring to water if X is the total amount of mixture. So how much flavoring do we have for X total gallons of mixture? Yeah, isn't it always 5 gallons of flavoring to start with? So then the question is, if you have X total gallons and 5 gallons of flavoring, then how much water is there? X? Yeah, so if we have X total total gallons of both and we want just the water, we're going to get rid of the, we'll subtract off the flavoring. So now for, what was the, so you want a table that represents this. So these arrows, the arrows indicate a sequence of numbers. So x is a sequence of numbers approaching 5 from the right. So what sequence of numbers could we do for that? So can I start with 3? So can I start with 4? What do I want to start with? Yes, so if it's from the right, it's greater and moving. So if you think of the number line, here's 6. We're going to move to 5 from the right. So 6, and then? Yeah, there's many possible answers here. So 5.5 is good. Then 5.1. Okay, and our function outputs the relative amount of flavoring to water. So it's this ratio that tells us kind of how much flavoring we have relative to how much water we have. So we always have 5 gallons. That's an amount. But what we're saying is we always have the 5 gallons of flavoring, but as the total amount gets closer to 5, what happens to the water amount? The amount of water does what?
Reaches 0.
Gets us really small, right? So if we get closer to 5 and we always have 5 of flavoring, then we're saying we're taking less and less and less water. So what will happen to that ratio of how much flavoring we have to how much water? Yeah, it'll get really big. So did you calculate these? What's 5.5? 10? 5.1. So what are we saying? We're saying that if you have 5 gallons of flavoring and 1/10 of a gallon of water, then the relative amount of flavoring to water is now 50. There's 50 times as much flavoring as water, right? And now if you only have a 100th of a gallon of water, then what's the relative size? You have 500 times the amount of flavoring to water. You see? That's what that ratio tells you. It's how many more times flavoring you have than water. So naturally, if you make that amount of water keep going down and down and down, is this 5,000? Mm-hmm. So that the relative amount of flavoring to water, as you decrease the amount of water, is just gonna skyrocket. You're gonna get a greater and greater multiple of flavoring to water as you take less and less water. Okay. So as x approaches 5, we can say, what does our ratio do? Is there a limit to this ratio of flavoring to water? No. So it approaches, goes to infinity, just like the last one. Okay? Again, this is the idea of vertical asymptote. So let's see it in action here. So there's 5. So I'll graph the first point. We'll just start with 5.5. There it is. Okay? Now if I want also total amount of 5.1, again, I've got to zoom out on that y-axis to start seeing these points. What are we doing? We are letting x approach 5 from the right. And we're tracking what the ratio of flavoring does, the ratio of flavoring to water. 5.01. One more, 5.001. So we're seeing the same behavior. And look at what's the root in the denominator. What is our root? X equals 0?
Plus 1.
Positive 5 is the root. And if there's a root in the denominator, that's where a vertical asymptote, and that's what we're seeing. So I can graph that. Okay, what's the domain of this function? What are possible values of total amounts of liquid? Yep, x has got to be greater than 5, right? It's going so fast it can't even. It's heading up to infinity so fast in this view you can't even graph it. So let's. There we go. That's good. Okay, so this is the idea of we have a vertical asymptote at x equals 5, and I'll do it light to show up. No, I'll do it black. Okay, it's the number. It's this kind of barrier. As we get closer and closer to 5, the graph can't cross it, and the values of the function, in this case the relative or the ratio of flavoring to water, will just get infinitely large the closer you get to 5. Okay, and where does that occur? At the root of the denominator. Where you're trying to make a 0 in the denominator, it's impossible. So the graph goes crazy, right? You're trying to do something that's impossible. Graph goes haywire. Okay, there will be I posted the written homework for Wednesday if you want to start on that, and there will be a short readings and workbook for Monday. Have a good weekend.